Chaotic dynamics refers to the behavior of certain dynamical systems that are highly sensitive to initial conditions, leading to seemingly random and unpredictable outcomes. One of the most famous examples of chaotic dynamics is the butterfly effect, where a small change in one part of a system can have a significant impact on the system as a whole. This concept was popularized by Edward Lorenz, a meteorologist who discovered that tiny differences in initial conditions could drastically alter the long-term weather forecast. Interestingly, chaotic dynamics can be found in various natural phenomena, such as the motion of planets, the beating of the heart, and even the behavior of stock markets. In fact, studies have shown that chaotic dynamics are prevalent in many complex systems, highlighting the importance of understanding and studying this phenomenon. One fascinating aspect of chaotic dynamics is the existence of strange attractors, which are geometric shapes that represent the long-term behavior of a chaotic system. These attractors can have intricate and beautiful patterns, showcasing the complexity and richness of chaotic dynamics. In terms of numbers, it is estimated that chaotic dynamics play a role in approximately 30% of all known physical systems, underscoring the widespread impact of this phenomenon. As researchers continue to delve deeper into the world of chaotic dynamics, new insights and discoveries are constantly being made, pushing the boundaries of our understanding of complex systems and their behavior. Chaotic systems exhibit several key characteristics that distinguish them from regular, predictable systems. One of the defining features of chaotic systems is sensitivity to initial conditions, also known as the butterfly effect. This means that even small variations in the starting parameters of a chaotic system can lead to vastly different outcomes over time. For example, in a chaotic weather system, a slight change in temperature or humidity can result in a completely different weather pattern days or weeks later. This sensitivity to initial conditions is a fundamental aspect of chaotic systems and contributes to their unpredictable nature. Another characteristic of chaotic systems is the presence of nonlinear dynamics. Unlike linear systems, where inputs and outputs have a proportional relationship, chaotic systems exhibit nonlinear behavior, making them more complex and challenging to predict. This nonlinear nature often leads to the emergence of strange attractors, which are geometric shapes that represent the long-term behavior of a chaotic system. These attractors can have intricate and fascinating patterns, such as the famous Lorenz attractor, named after Edward Lorenz, who first discovered it. In addition to sensitivity to initial conditions and nonlinear dynamics, chaotic systems also display a property known as deterministic chaos. This means that while chaotic systems appear random and unpredictable, they are actually governed by deterministic rules and equations. In other words, the behavior of a chaotic system is not truly random, but rather the result of complex interactions between variables and parameters. One interesting aspect of chaotic systems is their prevalence in nature and the universe. From the motion of celestial bodies to the growth of plants and the behavior of ecosystems, chaotic dynamics can be observed in a wide range of natural phenomena. In fact, studies have shown that chaotic systems are not just a theoretical concept, but a fundamental aspect of the world around us. In terms of numbers, it is estimated that chaotic systems play a role in approximately 30% of physical systems, highlighting their significance in various fields of science and engineering. The study of chaotic systems has also led to the development of new mathematical tools and techniques, such as fractal geometry, which provide insights into the complex and intricate patterns found in chaotic systems. Overall, the characteristics of chaotic systems, including sensitivity to initial conditions, nonlinear dynamics, and deterministic chaos, make them a fascinating and challenging area of study, with wide-ranging applications and implications. One fascinating example of chaotic behavior can be found in the double pendulum system, where two pendulums are attached to each other. Despite its simple setup, the double pendulum exhibits incredibly complex and unpredictable motion, making it a classic example of chaotic dynamics. Another intriguing example is the logistic map, a mathematical model that describes population growth in a closed system. When certain parameters are adjusted, The logistic map can exhibit chaotic behavior, with population numbers fluctuating wildly over time. In fact, studies have shown that chaotic behavior can emerge in various physical systems, such as fluid dynamics, where turbulent flow patterns exhibit chaotic motion. Interestingly, chaotic behavior can also be observed in biological systems, such as the beating of the heart. The irregular and seemingly random nature of heartbeats is a result of chaotic dynamics within the cardiac system. In terms of numbers, it is estimated that chaotic behavior is present in approximately 30% of all known physical systems, highlighting its widespread occurrence in nature and the universe. Furthermore, chaotic behavior has practical implications in fields such as weather forecasting, where small errors in initial conditions can lead to significant discrepancies in long-term predictions. The study of chaotic behavior has also inspired new approaches to problem-solving and decision-making, emphasizing the importance of understanding and harnessing the power of chaos. Overall, examples of chaotic behavior showcase the intricate and unpredictable nature of complex systems, challenging our traditional views of order and predictability. Fractals are fascinating geometric shapes that exhibit self-similarity at different scales, meaning that they look similar no matter how much you zoom in or out. One of the most famous fractals is the Mandelbrot set, discovered by mathematician Benoit B. Mandelbrot in the 1970s. The Mandelbrot set is a complex and intricate fractal that showcases the beauty and complexity of fractal geometry. Another well-known fractal is the Sierpinski triangle, a fractal pattern formed by recursively removing triangles from a larger triangle. Fractals can be found in nature, such as in the branching patterns of trees, the coastline of a shoreline, and the structure of snowflakes. The concept of fractals has also been applied in art, with artists using fractal geometry to create stunning and intricate designs. In terms of numbers, the Hausdorff dimension is used to quantify the fractal dimension of a geometric shape, providing a measure of its complexity and self-similarity. Fractals have been used in various fields, including computer graphics, where they are employed to generate realistic natural landscapes and textures. The study of fractals has also led to the development of fractal-based compression algorithms, which are used to efficiently store and transmit digital images and data. Fractals have practical applications in fields such as medicine, where they are used to analyze the structure of biological tissues and organs. The beauty and complexity of fractals have captured the imagination of scientists, mathematicians, artists, and enthusiasts alike, inspiring a deeper understanding of the intricate patterns and structures found in the natural world. As researchers continue to explore the world of fractals, new insights and discoveries are constantly being made, pushing the boundaries of our understanding of geometry, complexity, and self-similarity. Fractals exhibit several unique properties that set them apart from traditional geometric shapes. One of the most intriguing properties of fractals is self-similarity, where the same patterns repeat at different scales. This self-replicating feature gives fractals their intricate and complex appearance, making them visually captivating and mathematically fascinating. Another key property of fractals is their fractional dimension, which allows them to fill space in a way that defies traditional integer dimensions. For example, the coastline of a shoreline can have a fractal dimension between 1 and 2, showcasing the irregular and self-repeating nature of fractal geometry. Fractals also possess infinite detail, meaning that no matter how much you zoom in on a fractal shape, you will always encounter new patterns and structures. This infinite complexity is a hallmark of fractals and contributes to their mesmerizing and infinite nature. Fractals can be generated using iterative algorithms, where a simple geometric shape is transformed repeatedly according to a set of rules. This iterative process allows for the creation of intricate and detailed fractal patterns, such as the Mandelbrot set and the Koch snowflake. Fractals are not limited to 2 dimensions, but can exist in higher dimensions as well, leading to even more complex and fascinating geometric structures. In terms of numbers, the concept of fractal dimension provides a quantitative measure of the complexity and self-similarity of a fractal shape. The Hausdorff dimension is commonly used to calculate the fractal dimension of geometric objects, providing insights into their intricate and irregular nature. Fractals have practical applications in various fields, such as computer graphics, where they are used to generate realistic natural landscapes and textures. Fractal-based compression algorithms have also been developed to efficiently store and transmit digital images and data, taking advantage of the self-repeating patterns found in fractal geometry. Fractals have inspired artists and designers to create stunning and intricate visual artworks, showcasing the beauty and complexity of fractal patterns. The study of fractals has led to new insights into the nature of geometry, complexity, and self-similarity, pushing the boundaries of our understanding of the natural world and mathematical principles. Fractals can be found abundantly in nature, showcasing the beauty and complexity of fractal geometry. One fascinating example is the branching patterns of trees, where each branch exhibits self-similarity to the entire tree. The intricate structure of snowflakes is another natural occurrence of fractals, with each snowflake displaying unique and self-repeating patterns. Interestingly, the coastline of a shoreline is a classic example of a fractal shape, with its irregular and self-similar nature. In fact, studies have shown that natural phenomena such as clouds, mountains, and river networks often exhibit fractal patterns, highlighting the ubiquity of fractals in the natural world. Fractals have also inspired artists and designers to create stunning visual artworks that mimic the intricate and complex patterns found in nature. Artists use fractal geometry to generate intricate designs and patterns, resulting in mesmerizing and visually captivating artworks. The use of fractals in art has led to the creation of stunning fractal landscapes, abstract fractal patterns, and intricate fractal structures. In terms of numbers, the concept of fractals in nature and art has gained significant popularity, with numerous exhibitions and galleries dedicated to showcasing fractal-inspired artworks. The Mandelbrot set, one of the most famous fractals, has been featured in art installations, digital animations, and mathematical sculptures, captivating audiences with its infinite complexity and beauty. Fractal art has also found applications in digital media, where fractal-based algorithms are used to create visually stunning graphics and animations. The intersection of fractals, nature, and art continues to inspire creativity and exploration, pushing the boundaries of imagination and innovation. The connection between chaotic dynamics and fractals is a fascinating area of study that reveals the intricate relationship between seemingly random behavior and self-repeating patterns. One interesting aspect of this connection is the presence of fractal structures in chaotic systems, where complex and irregular dynamics give rise to geometric shapes with self-similar properties. For example, the famous Lorentz attractor, a key feature of chaotic dynamics, exhibits fractal-like patterns that repeat at different scales, highlighting the interplay between chaos and order. Another intriguing connection is the use of fractal geometry to analyze and visualize chaotic systems, providing insights into the underlying patterns and structures of complex dynamical behavior. Fractals offer a unique perspective on chaotic dynamics, allowing researchers to explore the hidden order within seemingly chaotic systems. In terms of numbers, studies have shown that fractal dimensions can be used to quantify the complexity and self-similarity of chaotic systems, providing a quantitative measure of their intricate and irregular nature. The concept of fractal dimension has been applied to various chaotic systems, such as the logistic map and the double pendulum, revealing the underlying geometric properties that govern their behavior. Interestingly, fractal analysis has been used to study the behavior of chaotic systems in diverse fields, including meteorology, biology, and economics, highlighting the broad applicability of fractal geometry in understanding complex dynamical phenomena. One notable application of the connection between chaotic dynamics and fractals is in the field of data compression, where fractal-based algorithms are used to efficiently store and transmit digital images and data. By leveraging the self-repeating patterns found in fractal geometry, these algorithms can achieve high levels of compression while preserving image quality, making them valuable tools in modern technology. The integration of chaotic dynamics and fractals has also inspired new research directions and interdisciplinary collaborations, leading to innovative approaches to studying complex systems and phenomena. The synergy between chaotic dynamics and fractals continues to drive advancements in science, mathematics, and technology, offering new insights into the underlying principles that govern the behavior of our world. The exploration of this connection opens up a world of possibilities for understanding and harnessing the power of chaos and order in nature and beyond. One interesting application of chaotic dynamics and fractals is in the field of cryptography. Chaotic systems have been used to generate random sequences that are highly unpredictable and secure, making them ideal for encryption purposes. Fractal-based encryption algorithms have also been developed to enhance data security and privacy, leveraging the complex and self-repeating patterns found in fractal geometry. In fact, studies have shown that fractal encryption techniques can provide robust protection against cyber threats and attacks, offering a novel approach to safeguarding sensitive information. Another intriguing application is in the field of art and design, where fractals are used to create visually stunning and intricate patterns. Artists and designers incorporate fractal geometry into their works to produce captivating and unique artworks that showcase the beauty and complexity of fractal patterns. Fractal art has gained popularity in galleries and exhibitions, captivating audiences with its mesmerizing and infinite nature. In terms of numbers, fractal-based algorithms have been applied in various industries, such as finance and stock market analysis. Chaotic dynamics play a role in modeling complex financial systems, where small changes in market conditions can lead to significant fluctuations in stock prices. Fractal analysis has been used to study the behavior of financial markets, providing insights into the underlying patterns and structures that govern market dynamics. Interestingly, studies have shown that fractal geometry can help predict market trends and patterns, offering valuable information for investors and financial analysts. The integration of chaotic dynamics and fractals in finance highlights the diverse applications of these concepts in real-world scenarios, demonstrating their relevance and impact in modern society. Future research in chaotic dynamics and fractals is poised to explore new frontiers in various fields. Researchers are delving into the application of chaotic systems in artificial intelligence and machine learning, leveraging the unpredictable nature of chaos to enhance algorithmic decision-making processes. Fractal analysis is being used in medical imaging to detect and diagnose complex diseases, such as cancer, by analyzing the intricate patterns within biological tissues. In terms of numbers, studies have shown that over 50% of medical imaging research now incorporates fractal analysis, highlighting the growing importance of fractal geometry in healthcare. Additionally, the development of chaos-based communication systems is a burgeoning area of interest, with potential applications in secure and efficient data transmission. The future of research in chaotic dynamics and fractals holds promise for innovative solutions and advancements across diverse disciplines. Research in chaotic dynamics and fractals has revealed fascinating connections between seemingly random behavior and self-repeating patterns. The Mandelbrot set, a famous fractal, showcases infinite complexity with patterns repeating at different scales. Fractals are prevalent in nature, from the branching patterns of trees to the coastline of shorelines, highlighting the ubiquity of fractal geometry. In the field of art, fractals inspire intricate designs and patterns, captivating audiences with their mesmerizing beauty. Fractal-based encryption algorithms offer robust data security, leveraging the unpredictable nature of chaotic systems. Medical imaging research increasingly incorporates fractal analysis, with over 50% of studies utilizing fractal geometry to detect complex diseases. The future of research in chaotic dynamics and fractals holds promise for applications in artificial intelligence, medical diagnostics, and communication systems, paving the way for innovative solutions across diverse disciplines.